Okay, so in the last few classes we have I think already started discussing about the FM bandwidth and we have also discussed FM modulation index. So, that is something we have already discussed, which is related to the frequency spread, and in the bandwidth also we have defined what is the relationship between the overall FM bandwidth and the frequency spread due to FM modulation, as well as overall the baseband bandwidth of the signal that is being modulated. Okay, so those things and Carson's formula for tone modulation, what happens to FM bandwidth, we have seen it from different angle and has started gathering information about what should be the FM bandwidth, and there was some fallacy around the calculation of actual FM bandwidth, that also we have discussed in detail. Now, what we will do is we will try to see how FM is being generated, and means what are the different options of FM generation, and then we will try to see how you can demodulate that. So, the means next 2 or 3 classes probably we will be discussing about FM modulation and demodulation, because we have seen that is the most important part. So, that is where the signals and systems actually interact with each other, and we need to define a system which does the proposed modulation or demodulation task. So, we will start with FM modulation. Okay, so that is the first thing, but before we start we should also characterize 2 things. Probably we have already started characterizing that. We have told that there are something called narrowband FM, which is called NBFM, and the counterpart of that is wideband FM. Okay. So, what is the narrowband FM? We have told that if the frequency deviation is very small, that means especially that KF value is very small, much smaller than 1. Okay. So, whenever this happens for our FM modulation, so corresponding FM is termed as narrowband FM, and we have also seen that Taylor series, with that Taylor series expansion of that FM modulated signal, we have seen that narrowband FM, when this particular KF into AT is much smaller, we can actually represent it as this. This is something we have already explored. Approximately can be represented as cos omega c t minus KF to AT sin omega c t, where omega c is the carrier frequency of that means with which we are doing that modulation, and what is AT, that is actually the means we for doing FM we have to first differentiate it, right, or integrate it for FM and PM. So, that is that part, right. So, this is what we have already discussed about that. Okay. So, this KF into AT, which is actually for FM, it should be integration, right, integration m alpha d alpha minus infinity to t. Okay. So, that is something which is already taken care of. So, m alpha, this is actually the message signal, okay, which we are trying to. So, that is actually we have told that there are, if you do Taylor series expansion, there are other terms which are being neglected because that will be, because of Taylor series expansion there will be KF square A square T and all other terms, because this is already very smaller than much smaller than. So, we are telling that KF AT is much smaller than 1. So, we can actually neglect that. Okay. Sin omega c t of course is bounded by 1. Okay. So, modulus of that. So, we are neglecting those terms as long as this is small. So, we get this particular things, and then we have told how then the narrowband FM that modulation looks very simple. It is almost like our this DSB-SC or amplitude modulation kind of thing, where you multiply this with this. Okay. So, if we just now put that, so what we have to do, we have this MT, whatever that signal is, we put through a integrator, we get AT, okay, and then we do our DSB SC modulation, where we supply actually a sine omega c t. So, basically we will have a oscillator which will be generating a cos omega c t, okay, and will give a pi by 2 phase shift to get sine, and then this has to be added. Okay, so plus this is minus, what you get is narrowband FM. Okay. So, it is easier enough, because what we have to just generate this a cos omega c t, which is coming from this path. So, we are getting a cos omega c t. Now, this is getting pi by 2 phase shifted. So, we get a sin omega c t multiplied by a t, and then we are taking minus of that. So, this plus and this minus. So, we get this particular thing. Okay. So, of course, we will say that somewhere kf has to be there. So, we will put a kf either over here, or we can include it over here. Okay. So, wherever you wish to take that kf, it becomes like that. Okay. So, this is how FM, narrowband FM, as long as whatever that kf you are choosing, that is small enough, and your means, or I should say kf into AT, that is small enough. Okay. If that is happening, you will not have too much of deviation, and the corresponding one, you do not really has to go and modulate the frequency with respect to the input signal, because we know that as long as that is small, we have that expression. Okay. So, immediately you will get FM modulation. For demodulation also, it is very simple, you just do the reverse process, because it is almost like AM modulation or FM modulation. Okay. So, right now we will not talk about FM demodulation. So, we are just talking about FM modulation. So, this is the way we will be generating, as long as the frequency deviation is small, this is the way we will be generating narrowband FM. Okay. If you have to just do PM, then you do not need this integration also, you directly supply it, right, MT you directly supply. So, MT will be supplying, and that directly goes into this DSB-SC. Okay. Rest of the things are same. So, this is that DSB-SC. Rest of the things are just duplication of this particular thing. Okay. So, narrowband FM, and that will be corresponding narrowband PM. Of course, you will have to again multiply with Kp. Okay, Kf for FM, Kp for PM, and that Kp into MT must be much smaller, otherwise we will not have that approximation. Okay. So, this is the generation process. Now, let us try to see what exactly is happening. I have this particular term, let us say phi FM t, which is a cos omega c t, minus kf a t sin omega c t, right. So, I have this. What is happening? This can be written as a sinusoidal. I can write it as E t cos omega c t plus some theta t. What is E t? That is actually, or I can write it as A E t. So, then E t should be 1 plus k f square A square t, right, because I am just trying to represent it as a cosinusoidal. Okay. So, accordingly we can put that, and this is what we get, because I can put that as sine, this as 1 as cos theta t, and then you manipulate it. Immediately we can also see that theta t will be just tan inverse kf into A t. So, this model means this particular representation we already know. Okay. So, from here to here, if we wish to represent, immediately A t and theta t can be represented as this. In FM, what we expected was something like A cos some phase variation, right. So, the amplitude remains the same, whereas in the narrowband FM, of course, there is a variation with respect to t of the amplitude. This is what we are getting. And the theta t, what we expected, suppose if it is FM, then generally theta t should be just this portion, okay, because theta t is omega c t plus this theta t. If it is original FM, this should be kf into integration m alpha d alpha, that is actually a t, integration of that from minus infinity to t. So, kf into a t you should be expecting inside the phase, right, because we want a frequency which is proportional to the message signal, whereas phase will be integration of that, right. So, this I expected, but what I am getting is, instead of getting it as kf at, I am getting tan inverse of that. As long as you can see already, as long as kf at is small enough, tan inverse of theta will be equal to theta. So, I have equivalent representation, and as long as kf at is much smaller than 1, I can actually make it as 1. Okay. But what we can also see from here means, however small this is, if this is not sufficiently small, then there is a time variation of the amplitude, however small it is, there will be. Okay. So, first task when I am generating FM, because I know whatever the frequency variation is, keeping that intact, can I make this amplitude constant? So, that is the first thing, because that should be the way FM is modulated. Okay. So, FM modulation, whenever I do that, amplitude must not vary with time. Here we have a variation, so we should be somehow employ something, some circuitry which actually keeps that amplitude fixed, while it will not touch the phase will remain the same. What is the process of doing that? So, whatever amplitude variation we have, so suppose a FM modulated signal, it might look like this. Something like that. Okay. Suppose it looks like this. Okay. So, there is a slight amplitude variation which should be generally constant. Okay, that should have happened, but that is not happening, let us say. If this is the case, what I can do, I can pass it through a special circuit which is called band pass limiter. What is this? This is first a hard limiter followed by a band pass filter. Okay. So, let us try to understand what is hard limiter. So, whenever that kind of signal is there, so suppose I have this, I have a VIT which is some AT cos, let us say some theta t. Okay. I am just trying to write that there is a amplitude variation, there is a theta variation. Okay. So, what it will do, it will, from this input it will generate a output VOT which is something like this, it will be +1 or -1 if this cos theta, whatever that is, that might be a variation of time and all those things, I do not care, as long as this cos theta is greater than 0 and okay. So, this is the hard limiter, that means I had this signal. So, whenever it is above 0, I must have +1 over there, and whenever it is below 0, I must have -1 over there. So, this should correspond. Okay. So, it is just almost keeping the frequency variation intact, but amplitude it is, because it is just making it +1 or -1. So, there is nothing in between. So, it is just making the amplitude constant. Okay. So, that is called the hard limiter. So, this is the output of that. So, whenever cos theta will be greater than 0, I have +1, whenever cos theta is less than 0, I will have -1. So, this is what will be the output. Okay. So, after passing it through a hard limiter, with respect to now, of course, there is a theta variation, but we can ignore that. If as long as we are plotting it with respect to theta, we can just try to see that what will be this output. Okay. So, this V output, if we say that is a function of theta, how does that look like? So, it is like this, it depends on that cos theta. If cos theta greater than 0, it is +1, and less than 0, it is -1. So, with respect to theta, if I plot, so it will be just with respect to theta, it is a square pulse with alternate plus and minus, right, with respect to theta. If theta has some other variation, I I do not know, because I am just plotting it with respect to theta. How theta varies with time, I am not plotting it with time, I am now just plotting it with theta. So, whatever the value of theta, it will just look like a square pulse having values plus and minus. So, that we have already represented. If you just think about that square pulse, we have already represented in Fourier series. Of course, we were saying that it is with respect to t, now we are doing it with respect to theta. So, if I just do that, if you remember that, we have already derived that. So, that should be cos theta minus 1/3, all odd terms will be there, or odd harmonics will be there, cos 3 theta plus 1/5 cos 5 theta minus dot 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 up to infinity. So, this representation we have already done that in our Fourier series analysis. Okay. So, as long as I have theta, V output theta must be represented as this, because that with respect to theta it looks like this, something like this. Okay. This is fine. Now, I can write what is this theta? This theta t is actually the overall FM modulated thing plus the carrier part. Okay. So, let us approximate that. This is actually omega c t plus, let us say k f integration minus infinity to t m alpha d alpha. Okay. I can write it this way. Okay. Of course, I do not have exactly this, I have some tan inverse of this one. Okay. Tan inverse of kf into at, I do have that, but whether I have that, I do not have that, let us say that probably this is the case. I can, instead of this, I can always write it is as tan inverse of kf into this, which is at actually, minus infinity to t m alpha d alpha. I even can replace this particular part as this, rest of the part will be remaining same, omega c t. Okay. So, this whole thing I can now write as 4 by pi, now cos of this, so which is omega c t plus, either I write it kf into this or tan inverse, whichever, let us take this one, it is just easier to write as long as they are similar, and then minus 1/3 cos, I will get 3 omega c t plus 3 kf, same thing. Okay. And so on. Now, all I have to do, I have told that my hard limiter, this is the hard limiter output, I have to pass it through a band pass filter which matches with the FM frequency, and the center frequency is omega c. Then what will happen? All these terms will be neglected. So, whatever I will be getting, that will be nothing but 4 by pi cos omega c t plus, in actual I will get tan inverse kf integration minus infinity to t m alpha d alpha, this is what I will be getting. Okay. So, that will be after passing it through a hard limiter and band pass filter. So, basically what I will do, I will generate a narrowband FM, then I wish to make the amplitude, before launching it I wish to make the amplitude constant. So, that is what I have done. Okay. So, here you can see that amplitude variation is gone. Okay. So, whatever amplitude variation it was having, that is all gone, I just have 4 pi, and of course, probably that A factor will be still there, that A will be still there, because that was already there in that. Okay. So, A factor will be there, and then I have cos this one, as long as tan inverse theta is equal to theta, I have FM modulated signal, okay, which will be happening if this is small enough. Okay. So, whenever we are generating narrowband FM, generally it is augmented by this, that band pass limiter. Okay. The reason is I can very easily do that. I will always have narrowband FM whenever I generate, I know there will be a frequency deviation which is little bit non-ideal of course, but as long as my kf is adjusted, that is correct, but there will be also a amplitude deviation which should not be there, and I have a very simple circuitry the way I have demonstrated just now. You can just employ that and you can make the amplitude fixed at least. and there might be any variation of this frequency, that is all right. You will also see if the amplitude variation is there, what is the consequence of that. We will demonstrate that also. Why we are doing that, that will be more clearer, but this is something you can do, and that is what the modulator chain will do. You will have first narrowband FM generator followed by a band pass limiter, and then you launch the FM signal. Okay. So, this is the way narrowband FM can be generated. Now, let us try to see historically what Armstrong did. He was actually taking that narrowband FM generated signal and then trying to make it wideband FM. Okay. So, let us try to see or appreciate how he has done that. Okay. So, that will be our first exercise. Okay. So, what he has done, so he has employed a method called indirect method. This is of course, we are targeting the FM modulation and doing it indirectly. That means, we will first generate narrowband FM, from there we will convert it to wideband FM, not directly generating it. Okay. We will also see what we mean by direct generation, but this is the indirect method. In the indirect method, what he started doing is started exploring some of the nonlinear devices. Okay. Let us see what happens. So, suppose I have a quadratic response nonlinear device. So, that means, if I have input x, so the output will be this. Okay. With diodes, transistor, you can realize this. With a particular biasing, you can actually get a region where it is nonlinear. Okay. So, you can do that. So, therefore, suppose I give you a narrowband FM signal, or let us say FM modulated signal. The corresponding yt should be like this. A2, my xt is cos omega ct plus, ideally it should be tan inverse that. I am just writing, as long as it is narrowband, we can even write kf. Okay. So, that should be my xt. Now, I put it over here. Okay. So, what will happen? I will have square. So, it should be cos square omega ct plus kf. Right. So, immediately what I can do, because it is cos square, I can have two terms. So, one will be half A2 plus, there will be another term which is half A2 cos 2 of this. So, I will get 2 omega ct plus 2 kf Now, you will be able to appreciate why he was doing that. So, what is happening? There is a 2 factor which has come over here, that something probably was not desired, but we will discuss about that. But what was desired was, there is a 2 factor which has come over here. Okay. Why this is desired? Because now we are actually going towards from narrowband FM to wideband FM. That means the frequency deviation has to be increased. So, what has happened? This will effectively increase the kf, and instead of kf it will become 2 kf. So, that means the deviation has become double. Whatever deviation I was having earlier in the narrowband FM, that is becoming double. Okay. So, it will keep on happening, and the good part is, if it is tan inverse, the 2 will be outside, remember that. So, this 2 remains outside, and then you will have this tan inverse, this kf into this part. Okay. So, inside tan inverse, it is still that narrowband FM. So, you can still approximate that to be kf into minus this, kf into integration minus infinity to t m alpha d alpha, right. So, this particular part remains intact, you are just multiplying, actually you are supplying terms, multiplicative terms to kf. So, you are slowly increasing that kf portion without hampering what was happening or what has been appreciated in narrowband FM. Okay. So, this was his method. What he did, instead of doing this, he went directly to nth order nonlinearity. So, basically he told, if I can get a circuitry like this, suppose it is A0, A1 xt, so it has nth order nonlinearity, and A2 x square t, we have just taken this term as if we have assumed A0, A1 and all other terms are 0. Okay. So, immediately if we just put it as whatever modulation we had, what we will get, and then rearranging them, there will be 2 of that whole theta t, 3 of that theta t, 4 of that theta t, rearranging all those things. I can just write it as C0 plus C1 into cos. Of course, the C0 C1 will be some, there will be some dependency with respect to A0, A1, A2, all those things. Okay. So, they can be, means there can be a corresponding equations. So, that will be cos omega c t plus of course, it should be generally ideally tan inverse. So, I can just write it that way, it is just tan inverse kf, let us write at only just for the brevity of it. Okay. So, tan inverse this plus some C2 into cos 2 omega ct plus 2, sorry, the kf should be there, oh, no, that is fine. Okay. So, this is that, then 2 into tan inverse kf at, right, and then up to Cn cos n omega ct plus n into tan inverse kf into at, right. This is what will be happening. Now, what I do, I need a FM which has n times deviation. So, I will put a filter around this. So, at n omega c, instead of putting it at omega c, I will be putting a filter around n omega c with appropriate FM bandwidth, because now the FM bandwidth will be recalculated because it has n times deviation. Okay. So, if earlier with narrowband FM it was del f, now it will be n del f. Okay. So, earlier if this was del f, now it should be n into del f. So, if I just put a filter over there, I will be getting just this term. So, that is actually a FM modulated signal, but what has happened, see this tan inverse this one can still be approximated as kf into at, because the original kf into at that remains still small, I can write that as kf at. Only thing is that gets n times multiplied. So, overall I get a wider band FM. Okay. This is the best part of it. Okay. So, that is what Armstrong did in a very ingenious way, and this particular technique is called as frequency multiplier. It is an indirect method, and you can see already it is doing nothing but multiplication of frequency, it is generating that. So, it is generating your FM modulated signal at n omega c, okay, with a deviation which is n times the deviation of the corresponding narrowband FM. Okay. So, with that understanding we will try to see what are the shortcomings of this thing. Okay. So, that is something we will try to analyze in the next phase or next class, and we will also try to see exactly in a practical scenario how do you design a FM transceiver, all this multiplicative factor, how we take into account. If we have a targeted frequency where the FM has to be put, that means some omega c is targeted, how do we actually manipulate that, because here something is not in our hand. We will explain that in the next class. Okay. Thank you.